for the introduction. Good morning, everyone, or maybe good afternoon or good evening, depending on your location. Let me start by thanking the organizer for giving me this opportunity to share my research in this beautiful conference. So today I'll be talking about arithmetic and statistics of sums of eigenvalues of Hecke operators. Today's story will go as follows. In the first part of the talk, we'll see about joint saturated conjecture and strong multiplicity one theorem. This is a joint work with Ramurthy. And in the second part of the talk, we'll see about the prime factors of sum of eigenvalues of Hecke operators. This is joint work with Ramurthy and Kumarmurthy. Although they may seem little bit different, but there are quite close connection. Okay, to start with, let me start with a question that can we classify the, just a second, let me just minimize this. Yeah, can we classify the space of modular form from the Fourier coefficients? And this question has been studied widely in literature in 1979 by Pitarsky Shapiro and 81 by J.K. Salaika. Let me set up the language also. We'll talk in this rest of the talk. So F1, F2 are two normalized Hecke eigenforms of different weight K1 and K2. E and Fi are the Fourier coefficient. For our convenience, we'll consider both of them a non-CM form for rest part of the talk. And BPFI, whenever we say normalized Fourier coefficient, that means we write the Fourier coefficient AP in this form, and we mean the BPFI. And they showed that if the normalized Fourier coefficient at prime indices matches for almost all prime, that means except finitely many, then one is going to be character twist of others. In 1979, Lewis and Lagrange, they conjectured that if the square of the normalized Fourier coefficient matches for almost all primes, then they are going to be a character twist of other, and the character has to be a quadratic character. And this conjecture was proved by Ramakrishna in 2000. In this direction, with the Ramurthy, we showed that if the normalized Fourier coefficient at prime indices where it matches, I mean collection of all the prime where the normalized Fourier coefficient matches has positive upper density, then one is going to be a character twist of other. So this density is just upper density. Note that the previous results are almost all prime. That means that except finitely many, and we have here positive upper density. So a couple of remarks about the result. Since we understand the Dirichlet characters very well, this with little restriction, this classify the space of Hecke eigenforms. This will also prove K1 equal to K2 if it satisfies the conditions. Rajan in 1998 proved similar result, but his method were more in algebraic, our is more in analytic in nature. And by modularity theorem, we can conclude similar result for elliptic curves over Q. To proceed further and to show the connection of this thing with joint saturated conjecture, let me set up a few notation. As we have seen already in our previous talk, that we can write the normalized Fourier coefficient from the work of Deligne as 2 cos theta pi. And this theta pi belongs to 0 to pi. They lies in the interval -2 to 2 by Deligne's work. So we can write them in this form. Why? Because if you just look at them as just a number, a real number in the interval -2 to 2, we cannot do much. But the moment we write like this, then we have our basic calculus or the trigonometrical identities we can use, as we have already seen in our previous talk also. So I won't give you a proof, but we'll just see that how this connect to joint saturated conjecture. So to prove the above theorem, we have to estimate this guy, theta p f1 minus theta p f2 equal to 0. And this is less than equal to f delta of theta p f1 minus f2 plus f delta of theta p f1 plus f2, where f delta is this following function. So what we have to note down here is there is something cost term involved here. That's all we will note, and we can forget about the F delta. Only thing we'll note is there is a cost term involved here. So we'll just put the value of F delta in the above inequality, and because this cost involves, and if we put this is like A minus B using this simple trigonometric identities, so we get product of two cost terms. Now again, this cost term can be written in terms of sign, and we can replace this cost term in terms of sign, and what we get is something like this. So we will forget all other term in this inequality. We'll focus on this sum only, where the product of cost involved. So basically, if we want to estimate this, that means what? We have to estimate product of this into this, product of this into this, this into this, and this into this. So in other words, basically we have to estimate something which involves product of two sine functions. In particularly this, so as previous F1, F2 are always our normalized Hecke eigenform, so that one is not a twist of others. Then to prove our theorem, we have to show that this guy is little o of pi x. And those who know, this is exactly the joint saturated conjecture stated in different form. There are several ways to see where this is joint saturated conjecture. And this can be proved by extending the work of Taylor, Harris, Sapper-Baron, Gerardi, Klogel, and Bernat-Lee by using their idea. The joint saturated conjecture can be proved. In fact, we have to use their idea in full force. As a hidden corollary of this result, I should write it as a corollary or probably as a theorem, that we'll note that from this we can conclude that P less than equal to X, such that APF1 minus APF2 equal to 0 is little o of X. And this is unconditional result. We'll keep this in mind, and again we'll come back to this result. Similar kind of result has wide application in many different ways. One is, as we already saw, like strong multiplicity one theorem. In horizontal, in the vertical setting where you fix a prime and you vary the form, so this kind of thing has a relation with something known as the Maida conjecture. Okay, so with this we'll go to our next session, which is normal number of prime factors of sums of eigenvalues of Hecke operator. In 1917, Hardy and Ramanujan showed that if you choose a random natural number n, then it has log n many distinct prime factors. More explicitly, they showed that if Wn is the number of distinct prime factors of n, then for any epsilon greater than 0, cardinality of n less than equal to x, Wn minus log n is greater than log n to the half plus epsilon. This is little o of x as x goes to infinity. In other words, the probability of a number such that absolute value of the number of distinct prime factors minus log n is greater than log n to the power half plus epsilon equal to 1. In 1934, Turan gave a much simpler proof of this fact, and in fact, his paper basically ignited the development of the subject known as probabilistic number theory. In 1940, in fact, Kark was reading his Turan's paper, and he noticed that this problem is basically belongs to the probability theory. And in fact, he wrote a letter to him saying that, using probability theory, it is possible to solve, and is it possible to calculate the higher moment also? And Turan replied saying that, although he can calculate, but he may not be interested because he doesn't see any application. But later on, Erdős and Kark computed the higher moment, and they wrote down this beautiful theorem, and they wrote down the distribution and what is known as the Erdős-Kark theorem. And this is actually beginning of the probabilistic number theory. In 1984, the Murthy brothers they proved an analog result for the Fourier coefficient of cusp form. Uh, so under a quasi-generalized Riemann hypothesis, so if APF is the Fourier coefficient of a cos form, and we are assuming that the Fourier coefficients are integer. In particular, if you choose the Ramanujan delta function, we know all the coefficients are integer. Then on average, on the distinct prime factors of APF minus log p square is O of pi x log x. So to prove this, basically they use the analytic representation theory developed by Delin and later on by Save, and they mix with this with the ideas of Turan, and they wrote down this proof. Maybe I should mention that they also obtained in the same year a Erdős-Kaik theorem type theorem for the Fourier coefficient of corresponds. Recently, in a joint work with Ramurthy and Kumar Murthy, we considered similar results for the sums of eigenvalues of Hecke operator, the sum of the Fourier coefficient of the corresponds. Note that whenever you consider the sum of the Fourier coefficient, the first thing you lose is the multiplicativity. I mean, this is no longer multiplicativity. That means what? You cannot use the whole multiplicativity theory for this problem. So first, what we saw that if F and G are two normalized Hecke eigenforms, weight 2. So let's stay in weight 2, but we can have for higher weight. Then on average, the sum is running over all the prime p, so that APF plus AGP is not equal to 0. So that the distinct prime factors of APF plus AG is pi x log x plus x pi log x. You also obtain the second moment of the same fact. Okay, so I'm going to describe briefly. I mean, what kind of things goes into the proof. We may not see the detailed proof. So to prove the above theorem, so we kind of generalize in some way the work of Hardy Ramanujan or later on Turan. So we axiomatize that suppose AP is a non-zero, I mean sequence of non-zero integers. For us, P is a prime. For some fixed A, so let us consider the growth of AP it has polynomial growth of P to the power A. For any prime L, we denote pi of XL is the all the prime less than equal to X, so that AP congruent to 0 mod L. And suppose that there exists a delta and some eta greater than 0, so that some pi of XL minus delta L pi X equal to less than X by log X. Moreover, assume that this delta L, what coming from the condition 2, satisfy this following condition. So if any random sequence of real numbers satisfy the above condition, first it is possible to show that on average, this is pi x log x plus O of pi x. So basically what this theorem is saying, this theorem suggests that on average, the normal number of prime factors of AP is log p. Moreover, with some few more notation, what we need to handle the sum of the Fourier coefficient, if L1 and L2 are two distinct prime, let us denote the pi of X L1, L2, which number of P less than equal to X, so that AP congruent to 0 mod L1, L2. And assume that there exists a eta 1, so that eta 1 lies in between 0 and eta. And we have this inequality. So if we have this extra inequality in hand, then we can obtain the second moment also of the random sequence AP. So to prove our theorem, basically we are going to use these results. So what we have to do, basically we have to show that the sum of Fourier coefficient has to satisfy this condition. So one is because we are dealing with the Fourier coefficients of Hecke eigenform, we don't have to worry about one. 2 is basically done in the Murthy's paper, their previous work, because we are dealing here with one Fourier coefficient. We have to worry about mainly 3 and 4. The condition 3 and 4. And to deal condition, I mean the one of the major tool comes to play here is the Chebotareau density theorem. As in corollary, I mean, we saw a glimpse of this Chebyshev inequality by using that Chebyshev inequality in the previous talk. By using that, we can obtain a corollary that for non-zero integer AP, like we considered earlier, and if we satisfy all the conditions, then this satisfies this condition. This is exactly like what Hardy-Ramanujan proved. Basically, we are obtaining the normal numbers. Okay, so we are going to see what kind of tools go into. Let me just say briefly what is Chebotareau density theorem. So if K by Q be a finite Galois extension with the group G, the map, the Frobenius map is equidistributed in the space of conjugacy class. In other words, what does it mean? So given a conjugacy class of given a conjugacy class C of G, the number of primes such that this sigma p belongs to C is asymptotic to the cardinality of C by cardinality of G into pi x goes to infinity. For our purpose, we need a effective version, and the effective version is due to the Orgil and Ramurthy, Kumarmurthy, and Sarada. So there is a effective version of this under certain restriction. So building upon the work of Delin, Serre, Ribet, Momose, and Loeffler, he considered the Galois representation of the image of the Galois representation of the product of rho f and rho g, where rho f and rho g are the corresponding elliptic Galois representation attached to f and g, and he studied about their image. So for us, I mean, we'll write in the language we need from the work of Loeffler. What we need is there exists a constant C of Fg such that the density of primes P which satisfy AP congruent to A mod L1 and APG congruent to B mod L2 is given by delta L1 into delta L2 B, where L1 L2 are primes greater than CFG, and the density of primes with APF is congruent to A mod L1 is the respective delta L1 A, and similarly for primes with APG congruent to B mod L2 is delta L2 B. So basically, we are going to use this to basically to count the density of the Chebotareau density of the primes, so that APF plus APG is a 0 in particular. Okay, to obtain that Chebotareau density, basically we have to compute certain cardinality. So this problem I'm going to convert into a group theory problem. So we have to count the cardinality of GL, where GL is the collection of tuples in GL2FL cross GL2FL, such that determinant of U equal to determinant of U prime. So this is because we are considering weight 2 actually. That's why in this case the things are a little bit easier. So we all know that how to compute this cardinality. This cardinality is L to the power 7 plus O L to the power 6. Moreover, we have to compute the cardinality of the subset, one of the subset of GL. We denote it as CL, which is the all pairs, so that with the extra restriction, that is trace of U plus trace of U prime equal to 0, and this restriction we already had earlier. So to compute this, basically we have to compute the conjugacy class of GL to FL. With this table, we have break into separate classes, and we compute it. This is easy to compute. So from the table, we can compute the cardinality of CL, which is L6 plus OL5, and knowing the cardinality of CL and cardinality of GL, now we can compute the delta L, which will be, if you put all this estimate, 1 by L plus O 1 by L square. So we denote SLX is the collection of or the number of primes such that APF plus APG congruent to 0 mod L. Now we use the effective version of Chebotareau density theorem, and we put all the estimates we have obtained earlier. And note that this guy will dominate the number of P such that this is equal to 0. We are now in a position to apply this thing to it satisfy all the estimates. So this thing earlier we have from the work of Murthy, but basically we have to remove from this estimate the collection of all the P for what this is equal to 0. This sum is equal to 0, and we denote them in terms of pi star. So with this notation and assuming a quasi-general Riemann hypothesis, basically this sum is with pi star where this has been removed minus delta L1 delta L2 pi x less than x log x. So to show this, basically we have to estimate a number of this prime, and which we write down a theorem, because this has very interesting application independent of all these results. So the number of p under a hypothesis, generalized Riemann hypothesis for Dedekind zeta function, the number of p is such that the sum either you take plus or minus equal to 0 is x to the power 6 by 7. So for sufficiently large x, this is x to the power 6 by 7. So note that in the previous talk, previous section, unconditionally we could show that this is just little o of x. But now with this restriction, this is x to the power 6 by 7. What does it mean? Actually, of the previous result in the previous section, the strong multiplicity 1 theorem. So without invoking the joint situated conjecture, but under this restriction, that means there is a different proof. If you assume here the automorphicity of all the symmetric power L function with generalized Riemann hypothesis, this we can improve to x to the power 3 by 4. Not beyond that. And the expected, if you assume the Lang-Trotter conjecture, this is supposed to be x to the power half minus epsilon. So with this, basically, we showed that we satisfy all the axiom and the result. Basically, we obtain. So a couple of remarks, I am almost done. So because this weight 2 forms are related to elliptic curve, so we have similar results for elliptic curve. So nothing special about AP plus AG, APF plus APG, but we can consider any P of APF into APG, where P is a polynomial into variable integer coefficient. From this technique, we can also Erdos-Craig theorem for the sum of this eigenvalues. Higher weight is a little bit complicated, but from the same technique, we can deal with them. But if you take more than 2 sums, this is a little bit complicated and turning out to be a group theory problem. But we are working on this to have a much general theorem. Thanks a lot for your kind attention.
Okay, thank you very much. So let's all virtually thank Sudhir for a very nice talk. So I'm afraid the next talk starts in 2 minutes. So I'm afraid we don't have time for Q&A.
Yeah, please, sorry about that. I took 2 minutes extra.
No worries. But please try and catch the speaker in the coffee break room, so you can ask some questions. So we have our next talks in parallel sessions in 2 minutes.